Okay, so last time we took a look at section 6.2, part 1. We talked about unit circle trig. We learned what the 6 trig functions were. Can anybody remind me, what are the first 3 trig functions? Just the originals, not the ones we flip.
Sine, cosine, tangent.
Yep, sine, cosine, tangent. How about the next 3 when we flip all those? Yeah, DJ?
Secant, cosecant, cotangent.
Yeah, you get the secant, the cosecant, and the cotangent. Right, so last time we studied unit circle trig, we looked at how to find trig functions if they give you a coordinate, or if the angle was 0, 90, 180, or 270. Okay, today we're going to find the 6 trig functions for angles that are either 30, 60, or 45. Okay, so we'll start in quadrant 1, and then we'll do multiples of those angles. Okay, so angles that are in quadrants 2, 3, and 4. But the only angles that we're going to do on the unit circle are multiples of 30 and 45. If it's not a multiple of 30 and 45, we're just going to use the calculator. Okay, and the last thing we'll do is we'll work a little bit with trig identities. Okay, so you guys did that on the bonus problem. We'll do a few more problems like that. All right, so the first thing we're going to try to do is figure out what the coordinates are for a 45-degree angle. Then we'll find the coordinates for 30-degree angle and 60. They're very similar. And then we'll practice some problems. All right, so let's start with our unit circle diagram. Okay, and in the circle, I drew a 45-degree angle. Okay, this is 90. It's 45 and 45. Okay, just so it's a little bigger, I drew it again down here so you can see it. All right, and our goal is to figure out the coordinates of this point. Just as a reminder, let's start with the coordinates for 0. Okay, what's the coordinates for 0 degrees? Brad?
1, 0.
1, 0. And somebody else remind me, what's the coordinates for 90?
0, 1.
Yep, 0, 1. Now, sometimes when I ask people the coordinates for 45, they say 1, 1. Why is that not right?
45 isn't all the way up.
Yeah, 45 is not all the way up at the top, nor is it all the way to the right. Okay, 1, 1 would be right 1, up 1. Okay, 1, 1 would be somewhere up there. It would be like the edge of a square if you're going to put that circle inside a square. Okay, so it's not 1, 1. It is 2 numbers that are the same. Okay, because this is, if you think about what kind of triangle this is, but it's not 1, 1. Okay, there is something that is 1 though. What's the hypotenuse in this triangle? That's 1. Okay, because it's the radius of a unit circle. And now we don't know the other 2 sides, but what kind of triangle is this?
The special right.
All right, it is a special right triangle. So is this one. But what's different about this one versus this one? This one is something else too.
It's isosceles?
It's isosceles, which means what about these 2 sides? They're the same. So what we can do, we don't know them, but let's just call them both x. This trick isn't going to work on this problem because these sides are different, because these angles are different. But for this problem, we can do this. And now, how could I solve for x?
X times x equals 1. Right? No, I mean x squared was. X squared equals 1.
X squared plus x squared equals 1.
Squared, yeah.
What is that?
The
Exactly.
Yeah, just plug this into Pythagorean theorem. You only have 1 letter. We'll just go through it. So x squared plus x squared. Technically, it's 1 squared, but that's going to simplify. What's x squared plus x squared?
2x squared.
Yep, we have 2x squared. It's good. I'm going to divide each side by 2. That gives me x squared equals a half. Last step, square root. And when you square root a fraction, you square root the top and the bottom. So we get 1 over the square root of 2. But what will that, when we fix it so we don't have the root in the bottom, what will that become? Brad? Good. Square root of 2 over 2. Okay. Any question on how we got x? Okay, so we're not going to go through that again. It's easier just memorize that. Okay, in a 45, 45, 90, the base and the height are both square root 2 over 2. Okay, so now let's write our coordinates. Okay, what did I just say the base is?
Square root 2 over 2.
Okay, you go over square root 2 over 2. And how about the height?
Square root 2 over 2.
It's also square root 2 over 2. That is always your coordinate for 45 degrees. Okay, so now if they asked us to find the sine or cosine, whatever they want, okay, we know x, we know y, we'll do that in a little bit. All right, what do you think would happen if I had 45, 45, 90? But this time it's going to be in quadrant 2. What do you think the only difference would be between doing it in quadrant 1 and quadrant 2? Yeah?
Would it be negative square root 2 over 2?
So the coordinate would be negative square root 2 over 2, comma,
Positive square root 2 over 2?
positive, yeah. And what would this angle be? In degrees? Yeah? That's 135. Because that's a 45. Quadrant 1 is a 90, plus 45 is 135. So you can have the 45 degree angle in quadrants 1, 2, 3, or 4. It's the same, well, how can I say it? Same x and y value, except the signs change. Quadrant 1, they're both positive. Quadrants 2 and 4, one of each. Quadrant 3, both negative. All right. So we'll practice that idea of flipping it into different quadrants. Questions on the coordinate for 45 degrees? Okay, let's look at the 30, 60, 90. So draw our unit circle. Okay, and this time 30 degrees, that's probably about right there. Okay, we'll make our triangle. And again, same thing I did last time. Instead of working with this small version of it, I'm going to draw it bigger off to the side. So that's my 30. And how do I know the top angle has to be 60?
Because 30 is 120, so 180 minus 120.
And all the angles in the triangle have to add up to 1. So that has to be your 60. Okay. Questions on the diagram so far? All right. What side do I know the length of in this triangle already? The hypotenuse, and how much is it? It's 1. It's the radius of the unit circle. Now, we can't do the same trick we did before. Okay. This time, I'd have to call one x and one y. But then the problem is you've got two variables. We don't want that either. Okay. So there's a trick here. I'm going to add something to this sketch to kind of help me. Does anybody know what I can add? I'm going to keep this part of it, but I'm going to add something to it, just temporarily.
You can make it like a rectangle?
Okay, we're not going to make it a rectangle. We are going to make it... I see what you mean, like if you added like a triangle up here.
Yeah.
We are going to make a copy of this, but we're not going to copy it
You're going to make
there.
Oh, you're gonna make
You're going to make
it
it half the side.
You're making an isosceles triangle?
Not isosceles, even. We're getting on the right track, though.
Equilateral scale.
Somehow we're going to make an equilateral triangle.
You already have 60 degrees there. That means you're saying 60 degrees.
You cut the...
So if you cut...
Can you say that
You're
again?
going to reflect it.
Reflect it, yeah, over the base. So just take, and again, this is just temporary. Take this triangle, just pretend like we reflected it.
Good job, Brad.
That's 30, that's 90, and that's 60.
Oh, yeah, isn't the hypotenuse like double the short side? Is it like...
Yes, the hypotenuse is double the short side, yep. So now we've got a 60, 60, and 60. Okay. So what kind of triangle is that?
Equilateral.
The big triangle is equilateral, which means every side is the same. So the side on the right is how long? 1. And now it's composed of two sides that are congruent. So two things that are equal that add up to 1, they both have to be how much? They both have to be 1/2. Now we can get rid of the bottom triangle. Okay, we just did that. We've got 2 out of 3 sides now. Now we can do Pythagorean theorem. Okay, any question on that? Let's just get rid of that. Okay, what can I call the bottom side now?
X.
Yeah, just call it x. So x squared plus a half squared equals 1 squared. Okay, what's 1/2 squared? 1/4. Okay, what does x squared equal? 3/4. Yeah, we subtract 1/4. And last step, we did this on the other one. Square root. This time it's going to work out nice. Take the square root of the top, you just get square root of 3. Square root of the bottom.
2.
Okay. Now we can write the coordinate for 30 degrees. Okay, actually, you know what? Let me squeeze it in down here. What's the horizontal, or what's the length of the base? It's the square root of 3 over 2. Square root of 3 over 2. And the height, 1/2. So there's your coordinate for 30 degrees. Now, let's say instead of 30, let's put the dot up at 60. How do you think the coordinate for this triangle is going to compare to the one we just had?
It'd be 1/2 and then square root of 3.
That's going to be 1/2 square root of 3 over 2. Okay, so what's happening in the taller triangle is now the 30 is at the top, the 60 is at the bottom. So if the 30 and the 60 switch places, all that means is x and y switched places. Okay. And the way that I remember it, the short side is the 1/2. Square root 3 over 2, if you type that in, it's 0.866. That's the long side. Short side is always across from the small angle. The longer side is across from the bigger angle. Okay, so 60 is bigger than 30. So root 3 over 2 always goes across from 60. Okay, and same idea, we can reflect into any quadrant. So let's say I had, let's take this triangle and flip it. What would this angle be, or what would the point be that corresponds to that angle? Negative what?
Negative 1/2, and then square root of 3 over 2.
Yep, negative 1/2. Perfect. Square root of 3 over 2. And what would be the degree of that? Yeah, that would be 120. So remember, this part is the big angle. This is 60 in here. So this part is 30 plus the 90. So we just found the coordinates for 120. Right, so you should be able to do, there's 3 in every quadrant. 30, 60, 45. So 3, 6, 9, 12. And then 1 on each axis. 13, 14, 15, 16. So 16 points we can do on the unit circle. Once we learn some more about trig identities, then you'll actually be able to do the multiples of 15, but we're not going to sketch them. We'll just do arithmetic to find them. But that's in a couple weeks. Okay, questions on the 30 or 60? All right. So let's just practice finding a few. For the first ones, I'll do all 6, and then we'll start doing less. Okay, so they gave me the angle. It's 45 degrees. If they give me the angle, what do I really need to find? Yeah, I got to get the coordinate. I got to get the point. Okay, so if we're in quadrant 1, I would just try to memorize those. They're the easiest because they're positive, positive. Okay, what's What's my coordinate for 45 degrees?
Square root 2 over 2, square root 2 over 2.
Yeah, square root 2 over 2, square root 2 over 2. And now the first one, we might need a little refresher on what these formulas are. But Tom, do you remember what letter sine is equal to? Y. And what's y here? Yep. How about cosine?
Square root 2 over 2.
Yeah, and which letter is that one? X. In this case, if you switch them, they're the same, but a lot of times they're not. So. And tangent, I like to think of just putting a divide in here. Tangent is y over x, which in this case would be 1. Okay, what do we do with the 3 on the left to get the 3 on the right?
Flip.
Yeah, just flip them. Okay. When you flip root 2 over 2 and get the final answer, what is it?
Square root of 2.
Over,
2.
it's 2 square roots of 2 over 2. And then the 2's cancel, and it's just the square roots.
So that's the same as that combination.
Yep. If sine and cosine are the same, secant, cosecant are the same. Cotangent? Yeah. That one's this. One is, when you flip it, it stays the same. Okay. So questions on how you find the 6 trig functions for 45? Mhm.
What was tangent? Was it x over y or y over x?
Tangent is y over x. Yep. So really, if we're going to write it out, it would be this. But if we divide two things that are the same, we just get 1. Yep. All right, let's try it for 30, and then we'll try it for 60. Okay, let's see. What's my coordinate for 30 degrees?
1/2. Square root of 3 over 2. No.
Does everybody agree with that? 1/2.
Or is it the other way
Square
around?
root
It's-
3
Oh,
over 2.
yeah, backwards.
Yeah. Okay, if you sketch it, okay, there's your 30. The base is the long side. Okay, so this is root 3 over 2. The height is the short side. That's a half. All right, so root 3 over 2, comma, half. All right. What is my sine? 1/2. Cosine? 3 over 2. And my tangent, okay, just think about what's going to happen when you divide them. What's going to cancel at least? The 2's cancel because they're the same denominator. So you have 1 divided by the square root of 3. And what does that become?
Square root of 3 over 3.
Yeah, if you multiply the top and bottom by root 3, you should get that. Okay. Steph, how about my cosecant? Yep. If we take a half and we flip it, there's no root. That one's not bad. Just 2. What about my secant? Think about flipping it, and then you got to fix it.
Square root of 3 over 3.
Good. 2 square roots of 3 over 3. Okay, any question on how we're fixing these? Just multiplying top and bottom by root 3 in this case, after we flip it. Okay, and for cotangent of 30, I have 2 things I could flip. I could flip the thing that's not circled or the thing that is circled. They're the same. Which one would be better to flip? Yeah?
The one that's not circled,
Yes, the one that's not circled. How come?
because it puts the 1 on the bottom and then just square root 3.
Yeah, and really importantly, it puts that square root 3 on the top, so then we don't have to fix it. If you flip the second one, that's fine. You're just going to get the square root in the bottom, then you're going to go through all the work and fix it. Okay. Any questions on the 6 trig functions for 30? Okay, and now when we do it for 60, Okay, since the coordinate just switches the x and the y, we're going to see all these same answers again. They're just going to switch places. Okay, what's going to happen is the co-functions are going to switch places. So sine will flip with cosine, secant will flip with cosecant, and then tangent will flip with cotangent. All right, so let's just write our point. Sine is now root 3 over 2. Cosine is a half. And when I divide these, the 2's cancel. And it's root 3 divided by 1, or just root 3. Okay, and we've already flipped all these before. So this is 2 root 3 over 3. This is 2. And this is root 3 over 3. Okay, any questions on how we got those? All right, so that pretty much covers everything we can do in quadrant 1. As we start to get into other quadrants, we're just going to do the first 3. I'm not going to spend all the time to flip them, just to keep us moving along. Okay, 135. Here's 180. Here's 90. Where's 135? Closer to 90? Closer to 180?
Closer to the middle.
Right in the middle. Which one?
Closer to 90. But close to the middle, but closer to 90.
Do you think it's a little closer to 90?
Yeah.
Well, let's just check. Let's find out what's exactly in the middle.
Oh wait, no, I lied. I'm sorry, I'm thinking of 120.
If you add them up and divide by 2,
I'm thinking of 120.
120. Yeah, that is an angle we could do, but this one is right in the middle. Okay, so your 45s are 45, 135. What's this one? 225. And then this one?
No, 315.
315. Okay, so it's helpful to know those 45s in each quadrant. All right, so we know we got a 45, 45, 90. So that tells us we're dealing with the root 2 over 2's. Just be careful with the negative. Okay, Corey, what's my coordinate here?
So that would be negative 2 over 2.
That-
2 over 2.
Left and up. Good. Okay, now it's important we don't mix up x and y because they're different. Right, so Heaven, what's my sign?
Square root of 2 over 2.
Yep. Square root 2 over 2. Okay, Shelby, my cosine.
Negative square root of 2 over 2.
And how about my tangent? Yeah, we're dividing two things that are the same except for the sign. Negative 1. Okay, questions on finding sum of the trig functions for 135? Okay. 7 pi over 6. Okay, if you're not sure where that is, what would make this easier to find on the circle?
Calculator?
No, we don't need a calculator.
Convert it to
Yeah, it's easy to change to degrees. What's pi over 6 in degrees? 30 times 7. 210. Okay, so that's 210 degrees. All right, this one we might want to draw just to see where the 1/2 and the root 3 over 2 are going to fall. I know that this is a multiple of 30, that's why I said those two numbers. This is not a multiple of 45. Okay, this time, am I going to be closer to 180? Closer to 210?
180.
Yeah, closer to 180. So here's my triangle. The shorter side is always how long? That's always my 1/2. And the longer side, not the hypotenuse.
Negative 2/3. Well, 2. I mean, 3 squared over 2.
You can consider it 3 over 2.
Square root 3 over 2.
That's what I said. What did I say?
No, you said like 4 different things.
Now, those are correct. Just be careful when we're in quadrant 3. Both of them should be
Negative.
negative. So negative, which one comes first?
Square root 3 over 2.
Yep, x first. And then down, that's my y, a half. Okay, once we have those, it's the same as what we've been doing. All right, so how about, Maddie, what's my sign?
Negative 1/2.
Yep, negative 1/2. Okay, Brad, my cosine?
Negative 3 over.
Square root 3 over. Yep, perfect. Okay, and my tangent? Okay, first, let's do it in 2 steps just so we don't lose people. What cancels when you divide these? 2's and the negatives. Okay, so you'd have 1 over the square root of 3
Square root 3
over 3. Okay, any questions on finding some of the trig functions of 210? All right, does anybody need any other examples of, we didn't flip it into the 4th quadrant, but okay. All right, so make sure you know all 16, 3 in each quadrant, and then 1 on each axis. Those are the easy ones on the axis. Those are your 0, 1, 1, 0, negative 1, 0, all that stuff. All right, so if we have a problem where they're asking us about something that's not a multiple of 30 or 45, we're going to use the calculator. So we'll just use the calculator. All right, so let's just start off by finding sine, cosine, and tangent of 42. Okay, you don't need a graphing calculator. Any calculator works fine. Okay, what's the first thing that I want to check before I even type this in? Something I need to be careful with. Yep, on my calculator. Yeah, I should make sure I'm in the right mode. Am I in the right mode for this problem? I'm in radians. So is that what I want? I should be in degrees. Okay. So first thing I got to do is change to degrees. Okay, that's the simplest mistake I see on these problems. On the test, people accidentally leave it in radians and it's wrong.
How big a difference does it make?
Right versus wrong. So.
Is it the math still the same?
Oh, you mean the answer itself?
Yeah.
It can be pretty significantly different. Anytime you take sine, the answer is always between 1 and negative 1. So it can't, you can only get as far apart as those 2 numbers. But again, if you're just a little off, it's wrong. Okay, so here's sine 42. It's set to round to 2, so we go 0.67. Okay, how about cosine 42? Anybody have that one?
0.74.
Point what?
0.74.
Yep, round that down. And tangent of 42?
0.90.
Yes, 0.90. Make sure you do show that accuracy if they ask for 2 decimals. Okay. Now, the other 3, we don't have buttons for. Okay. Sometimes people suggest, well, what about second sine? That's something different. Anybody know what that is? That's inverse. Okay, we're going to talk about inverse sine, but not today. So how would I get cosecant 42 on here?
Take what you have and just put it on.
Yeah, so all we have to do is flip it. Okay, instead of finding the cosecant of 42, we're going to do 1 divided by the sine of 42. Now, I already know the sine of 42 is 0.67.
What percent of it? 0.32.
This one?
Don't they like equal 1 when they're together?
No. No, they don't add up to 1. I know what you're talking about, but that's actually something to do with these 2 when you square them. This squared plus this squared would equal 1.
Wait, I thought you could just do second side. 'Cause
No, what did we just say about that second sign? That's inverse. Okay, it's confusing because it has a -1, and you usually think, oh, well, -1 means to flip, but in that case, that -1 is not an exponent. So what's really weird is if you write this versus this, they're not the same thing. Yeah, this means inverse sign. This means that, which are not the same thing.
So if we take the sine of a number and then multiply by the negative,
Well, these are powers.
I mean power.
Yeah.
The power of -1 would it be, right?
Yeah, if you typed it in like this on the calculator, it would work. Yep. But what's really strange is if you type in this versus this, those are the same thing. So anytime your exponent is -1, this is just a symbol for inverse sign. Don't think of this as an exponent. If it is a number other than -1, it is an exponent. Okay, just the way it works. All right, so the reason I didn't type in 1 over 0.67 is because that's rounded. Okay, always just go back to the original, and you should get about 1.49. Okay, how about secant 42? How would I type that in?
1 divided by cosine 42.
Yep, 1 divided by
Take the sine.
cosine 42, so 1.35. And lastly, cotangent 42.
1 divided by tangent 42.
1 divided by tangent 42, 1.11. Okay, so any questions on that? Okay, what's big difference between this problem, which we're only going to find 2 of them, and the one above? Besides the fact we're only finding 2 trig functions instead of 6. It's in radians. Okay, so if you just type in sine of 10 right now, it's wrong. Okay, first thing you got to do is go to mode, go to radians. Now we're all set. Okay, what is it? 10. Okay, so sine of 10, negative 0.54, and cosine of 10.
Wait, so
Oh,
why
that's gonna
did
mess me
we
up so
turn
much.
that to radians?
What's that?
Why did we turn that to radians?
There's no idea.
We changed it because that doesn't have a degree symbol.
This is going to screw me so much.
So make sure, just look at the problem carefully. Okay, if you see the circle on it, then you know we're in degrees. If you don't see the circle, you got to switch to radians.
That's compass.
Yep, same.
Yeah, you got to be careful and pay attention. Okay. Questions on that? All
You
right.
said you don't need a graphing calculator, but technically you do.
You need a scientific calculator.
So if you do it with a
You don't have to
scientific
graph this.
calculator, if you do it with a scientific calculator, you have to change the load still.
Yeah. Yeah. So if I was going to do cosine of 10, I got to make sure I'm in radians. Anytime you press sine, cosine, or tangent, the answer that comes up on the screen is going to be affected by what mode you're in. Okay. If you just do arithmetic, like
That's
add,
correct.
subtract, multiply, divide, it's not affected by the mode. Mode's only affected if you press these buttons, trig functions. So here you type in 10 sine, and I get negative 0.54.
What does it say, sine R?
Sine R? Oh, right here, sine H?
Sine radians.
No, like.
No, it says sine radians.
Oh, yeah. This calculator tells you that it did sine in radians. If it said sine D, it would be sine in degrees.
What's the grads?
Radians. It's another way to measure angles, but we don't use it.
Wait, so what's the side each then?
Sine H, we don't use that either.
What are the,
Stands for hyperbolic sine.
That's
Yeah.
just-
We don't use it. Okay, maybe in calculus you'll talk about hyperbolic trig functions, but we don't in pre-calc. All right, so that last problem where we had to flip things, that reminds us of the connection between sine and cosecant, cosecant, secant, tangent and cotangent. They're reciprocals of each other. Okay, and these are called the reciprocal identities. Okay, what I would do is if you're writing these down, we're going to have a bunch of identities we learn over the next month. It's helpful to put them all on the same page. Or you can just highlight them or put a box around them, but it's nice to have them all in the same spot. Okay. Even today I've got 5 more I'm going to add to these. So at least for today, leave some room below so you can add 5 more. All right, so these are called the reciprocal identities. If you flip sine, you get cosecant. Flip cosine, you get secant. Flip tangent, you get cotangent. Now, if you flip them again, you change it back to what you started. If you flip cosecant, you get sine. Flipping secant gives you cosine. And flipping the cotangent gives you tangent. Okay, so we're going to talk more about some basic, these are called fundamental identities. Okay, these are ones that eventually you should have memorized. And we'll talk more about these in a little bit. Okay, but first I just want to talk about some special properties that only really apply to sine and cosine. Okay, sine and cosine are different kind of trig functions than the rest. Okay, when we graph them, the graph is a lot nicer. It's a nice connected function that's a wave. Every other trig function, tangent, cotangent, secant, and cosecant, the graphs aren't as nice. Okay, they're disconnected, they have asymptotes in them, but sine and cosine do not. Okay, does everybody have the reciprocal identities? All right, so let's just take a look at some special properties for sine and cosine. Okay. First of all, when you graph it, let's just look at a picture. Okay, it goes left and right forever. Bless you. Okay, never stops. So the domain is negative infinity to infinity. But there is a limit on how high and how low it goes. Yeah. Okay, both sine and cosine only go as high as 1 and as low as negative 1. Okay, if you want to see what cosine looks like, it's basically the same function as sine, except what would you say? It's been what?
Shift.
Yeah, it's been shifted. Okay. Yeah, however you want to look at it. Take sine and shift it to the left, or take cosine and shift it to the right. But notice, same heights, 1 to negative 1. Right, and because of this repeating kind of nature of the graph, these y values keep repeating. How often do they repeat? Every 360 degrees, or every 2 pi. Right? So in other words, this point right here, if I add 2 pi to it, or 360, it's going to go right here. It's going to be the same y value, just further down the graph. If I add 360 again, it's going to be right there. Right? So if I type in, let's just try something in degrees. Okay, here's the sine of 10. Okay, you get about 0.17. So imagine that's this middle dot right here. Now if I add 360 to it, 10 plus 360, what do you think I'm going to get when I hit enter? Which will come out to what? Yeah, it's going to come out to the same as the sine of 10. Okay, they're the same thing. Right? All you've done is you basically moved one section down the graph. Okay, this graph repeats itself every 360 degrees. This section right here, we call one period of the graph. If you take what I just did in red and copy and paste it left and right forever, you'd get the entire graph. Okay, what if I did sine of 10 minus 360? It's going to be the same thing. So now we're looking at the same y value, we're just moving to the left. Okay? I can add or subtract 360 or 2 pi as many times as I want. Okay? And that answer always stays the same. Okay? It's kind of like if you're on the unit circle. And I said, where am I going to land if I add 360 degrees to that point? Right back where I started. Okay? Similar idea. This idea works for sine and cosine. Okay, and that's called the periodic property because it's based on the period, or in other words, how long before the function repeats of sine and cosine. Okay, so that's the periodic property of sine and cosine. Okay, the other trig functions have periodic properties as well, but they're not all 2 pi. Okay, tangent and cotangent, those are a little different. Okay, we're not going to look at those today. Okay, so any questions on that idea? All right, so also talk more about this when we solve equations. What does that mean? If I say can find one solution that makes a trig equation true, how many solutions are there really? How many? Infinite. Yeah, if you can find one solution, you can find infinitely many, because that solution you just found is going to reoccur every 360 degrees, or every 2 pi radians, forward and back. All right, so last thing we're going to look at is those trig identities. Okay, I'm going to add to that list that I gave you. But just a reminder what an identity is. It's an equation that's true for all appropriate values of the variable. Okay, there are some trig functions where values are not appropriate to plug in. For example, this is not appropriate. You can't plug 90 into tangent. It's undefined. Okay? So when I'm talking about identities, I'm talking about it's true for all numbers you can actually use, not numbers that are not in the domain. Okay, and we're going to look at what are called the fundamental identities. So you've already got the first 6. Okay, inside probably any calc book, I know the one you use next year, you'll find probably a page in the front or the back with hundreds of identities. Okay. The idea is you don't memorize identities, you look them up. Okay, I'd say that there's probably like 12 to 15 you need to know. This is 6 of them right here. The other ones, when we need them, we just reference it and we use them in a formula. Okay, so I'll show you kind of the algebra part of what we're going to do with identities. And then I'll talk a little bit about how you might use that in calculus. Okay, but the part I'm about to show you right now, next year Mr. Bad probably won't go over the algebra part. So you need to know what I'm showing you right now. Okay, so 2 other identities, which I think we've mentioned. Sine over cosine is tangent. Cosine over sine is cotangent. And the last 3 I'm going to put up are called Pythagorean identities. We're not going to use them today, but they are part of the fundamental identities. So I wanted to kind of get all of these in one section. Okay, so you get your reciprocal, your tangent and cotangent, and your Pythagorean. Okay, so your Pythagorean are sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And 1 plus cotangent squared equals cosecant squared. Really, these other 2 are all derived from this top one. So if you can just remember sine squared plus cosine squared equals 1, you can figure out these other 2 if you have to. In fact, one of the homework questions says to take sine squared plus cosine squared equals 1 and somehow get this identity. At this point, I think that's a little bit of a tough question because we haven't worked a lot with identities, but we will later on. Okay, this is just showing the point I was trying to make. I think it was Shelby asked earlier. These are the same thing. Okay, usually when we raise a trig function to a power, we put the number right in between the argument and the trig function. Okay, the only time we don't is when we have inverse trig. The number you put in there is not an exponent. It's just the way it is. Okay, so we're gonna focus on those 8 today. Those 8 identities. Okay, does everybody have identities? Yeah. Okay, we'll keep that up. Okay, now we can take identities and rearrange them. So these two are not different. All you did here was take and subtract this and put it on the other side. Rearranging an identity is not a new identity. Okay? Kind of like if you had x plus y equals 1, and then somebody said, oh, well, y is 1 minus x. Well, the first equation tells me that. It's the same thing, just rearranged. And a lot of times when you get a problem, when we get into Pythagorean identities, you have to look for them rearranged. Okay? Maybe something moved to the other side. And lastly, these top 2 sections of identities, not the bottom. Just the top 2. You can use them with higher powers. All right, so we said that cosecant is 1 over sine. What do you think cosecant squared would be? It would be 1 over sine squared. How about cosecant cubed? That'd be 1 over sine cubed. We generally don't go into powers that are this high, but you could. How about if I had sine squared divided by cosine squared? What do you think that one would be?
Tangent squared.
Yeah, that would be tangent squared. Okay, it's the same identity. It's not really a new identity. You're just doing it with a higher power. Okay, and the whole goal with identities is to take an expression that looks complicated and make it simpler. Right? So in calculus, you might be asked to differentiate or integrate. Those are 2 things you'll learn how to do. This expression. Well, when you're differentiating and integrating, there's different rules, and the more complicated your expression, the harder it is to do. So if we can use algebra to simplify this before we start doing the calculus stuff to it, then the calculus stuff is a lot easier. Okay? We can do this without algebra. Okay? We don't have to do what I'm going to show you right here, but it makes things a lot easier. It makes the calculus part easier. Okay? So my goal is to basically use substitution. Change cosecant to something in this list. Change tangent to something in this list. And hopefully we get something canceling out. Again, today, these are not going to come up. So don't use the Pythagorean identities. Okay, one trick that is helpful is to change everything to sines and cosines. So how can I write cosecant using either sine or cosine?
1 over sine.
Yep, that's 1 over sine. And now tangent, if you look on your list, there's 2 ways you can write it. I would like to write it using sines and cosines. How do you know to do it that way and not the other way? Practice. So it cancels out. You're trying to cancel things out. And if you write it as 1 over cotangent, that's not going to help. We're going to get stuck. So how would we write tangent? Sine over cosine. And what cancels out? So I'm left with what in the top? 1 in the bottom? And what is 1 over cosine? That's also in your list. Secant. So now, if we have to do some kind of calculus thing to this, we just have a single trig function. we no longer have a product. We just made it a simpler expression to work with. Okay? But for us, we stop with the algebra part. Okay, any questions on that? Okay. Sometimes they don't all simplify this nice. Okay, today I'm going to give you ones that do simplify nicely. And all the ones today are what we consider easy. These are very easy identities. Identities can get insanely hard. We don't do any in this class that are too hard, but they can be very, very challenging. All right, secant times cosine. Any suggestions what I do here? Brad?
Put 1 over cosine.
Change that to 1 over cosine. How about the next factor? Do you want to change that?
Cosine over 1.
Yeah, we'll just leave it as cosine over 1. And what happens there? Cancels out, and we get 1. So basically, this says if you multiply something by its reciprocal, you just get 1. Okay? It doesn't always simplify to just a single number, but now, if we have to do something with this is super easy to work with. It's just a number. It's not even a trig function anymore. Okay? Any questions on that? Okay, and let's take a look. This will be our last one. Cotangent divided by cosecant. Right, so when you're doing identities, sometimes I kind of make an analogy between this and like playing chess. Sometimes you want to see a couple moves ahead, like what you're going to try to get to cancel out down the road. And that tells you what you want to do now. Okay, so it does take a little practice to see what's going to cancel out here. But changing to sines and cosines is always a good idea.
Would you have to change the cotangent to 1 over tangent, maybe?
You could change it to 1 over tangent. I just don't think we're going to get anything to cancel when we change this later on. So what's another way we could change cotangent?
Cosine.
Yeah, and that's the way you want to do it this way. You'll see in a second.
Oh, I didn't think about that. Okay.
Now what's cosecant?
1 over
That's 1 over sine. And now what cancels out?
Yeah.
And what are you left with?
Cosine.
Just cosine. Now again, the way you wanted to do it, again, not wrong, I just think we're going to get stuck. And sometimes there's more than one way to get the final answer. These identities are so easy that there's really one way to do it. Okay, harder ones, there's multiple ways. Okay, any questions on that? All right. So homework tonight. It's a lot of just short little pieces of the section, but it's page 335. 13 to 17, 21 to 25, 29 to 32, 37 to 40, 45 to 47, 50, 55, and 56. And try to simplify this identity. Secant squared over tangent squared. If you get stuck, pretend it was secant over tangent. Do that first. And then secant squared over tangent squared, almost the same idea. Okay, I circled 50 because 50 is, that one's a little hard. It asks you to show how one of the Pythagorean identities comes from sine squared plus cosine squared equals 1. It's actually just one step. But if you have trouble with that, if you don't get number 50, don't worry as much about number 50. We'll do that in class together.